Building Construction, Week 6, Homework Problem 2. Here you're asked to find forces and reactions in this truss member, and the fact that this is a truss is significant because remember that trusses have structural members that are only loaded in pure axial tension or compression. There are no moments developed in the individual components, and or I should say there is no bending stress developed in the individual components, which is going to greatly simplify this problem. As you can see, it's pinned at point A and there's a roller at point D. And remember, the characteristic of a roller is that a roller is not able to offer any reaction in the direction in line with the rollers. That is to say, if I were to push to the left or right on point D, it would simply roll away. That's useful to me because I look at the horizontal forces in this structure and I see that I have a 4,000 pound pull to the right at point C. Well, the only thing in this structure that can provide a horizontal reaction to that is point A. And so I know that there has to be a 4,000 pound leftward force at point A. Now, to figure out the rest of this, I think the next easiest place to go is to point D, and I'm going to start thinking about moments about point D. So I can use my fundamental formula for static equilibrium that the sum of the moments about point D equals, and then I'm going to start counting up moments. Well, there's this 5,000 pound downward force that is 5 feet to the left of D. And so when I put that in, I'm going to think of that as negative 5,000 pounds because it's to the leftward direction times negative 5 feet. It's a negative 5,000 pounds because it's downward. It's negative 5 feet because it's to the left. Plus, now I want to think about this 4,000 pound load. This is to the right, and it's above D, which is going to have a tendency to create a clockwise rotation. Well, remember that in the Cartesian system, a clockwise rotation is considered a negative movement. So I want to conceive of this moment as being negative. So I'm going to think about this as like negative 4,000 pounds times the length of this lever arm, which is 5 feet plus 1 foot, 6 feet. So that if you look at this first moment here, it's a negative times a negative. That's going to give me a positive number. And that makes sense because this is going to produce a counterclockwise moment. This is a negative number times a positive number. That's going to give me a clockwise rotation, or a positive moment, which makes sense because this lever arm tends to produce a positive torque. Now, if you think about this, let's crunch the numbers once. The first moment is 25,000 pounds, 25,000 pound-feet in the counterclockwise direction, so it's expressed as a positive number. The second number here is negative 24,000 foot-pounds, and again that indicates clockwise direction, the fact that it's a negative number. Well, you can see that these don't cancel out. There must be something else creating a moment here, and the thing that is creating the moment is this point A. And so when I think about point A, it's going to be the force in the y direction at A times the length of this lever arm from D to A, which is 4 plus 1, which is 5 feet. Now, what do all these moments need to sum to? They all have to sum to 0 for this to be in static equilibrium. So as I start looking at this, I get negative 1,000 plus 5 times the force in the y direction at point A equals 0. If I push this around a little bit, 5 and times the force in the y direction at point A equals 1,000. And the force in the y direction at point A equals 200. Now, this is going to take a little bit of thought as to should this be, does this 200 pounds mean that point A is pushing up on the structure with 200 pounds, or does it mean that the structure is pushing down on point A with 200 pounds? Well, because it's a positive number, that's an indication that point A is pushing up on the structure with 200 pounds. Now, from that, I can work a few other things out. One of the things I can work out is if I think about the sum of the forces in the y direction. So if I do sum forces in the y direction, well, they equal this negative 5,000 pound weight plus this 200 pound upward reaction at point A plus the force in the y direction at point D. And what do they all have to add to? Again, they all have to add to 0. So I can probably just solve this by inspection. If I have a 5,000 pound downward force here, straight down onto point A, and point A is only pushing back with 200 pounds force, that means that point D has got to be providing the remaining 4,800 pounds force, which is maybe a little bit counterintuitive, but what allows for this is the fact that we've developed this large moment about point D. So we've got our reactions at point A and point D. If I were to draw free body diagrams of point A, I've got a 200 pound upward force or an upward reaction at point A. I have a 4,000 pound leftward reaction at point A. At point D, I can't have a leftward or rightward reaction because it's on a roller. I simply have this 4,800 pound upward reaction. So that's the first part of this analysis, is that we want to think about the support reactions, which we've just calculated. Now, the force in CD, this is a little bit more complex. I have to start thinking about point C, and I got to think about the moment in part in component BC. And if I look at this, this 4,000 pound pull to the right, acting on this 1 foot lever arm, is going to tell me that I'm going to create this negative 4,000 pound foot moment about point B. And the question is, how hard does component CD have to push up to cancel that moment? Well, this is a little bit sticky because we aren't sure that CD is perpendicular to BC. And so that's the first thing we want to work out. So I'm going to clear the existing work that's already shown on the screen here, and we're going to determine the angle between component BC and CD. So if I start thinking about angles here, I can figure out this angle between the horizontal line and CB using the inverse tangent function. So if I start thinking about like this angle right here, well, what do I know? I know that the adjacent side to this angle is 4 feet and the opposite side is 1 foot. And if I think about the function that relates opposite, adjacent, and angle, it's the tangent function. But you'll notice here that I'm starting out knowing the length of the sides, not the angle. So I'm going to turn the crank backwards on the tangent machine. So tangent minus 1, or you might see this as arctangent, opposite over adjacent. The arctangent of 1/4 is going to equal the angle at C. Okay, that's this angle. Now, this is useful because if I draw in another horizontal line, by property of parallel lines, this angle I can tell is the same as angle C, which tells me the direction, tells me the heading of this piece in the Cartesian plane. So its absolute angular coordinate is going to be the same as the number I get for point C. For component CD, I'm interested in this angle. And if I think about this angle, again, I have this adjacent side, which is 6 feet long, right? 5 feet and 1 foot. And I have this opposite side that's 1 foot. So if I think about angle D, I can get that by saying that it is the arctangent, or the inverse tangent, opposite over adjacent, 1/6, equals angle D. Now, if I think about the heading of this component, it is actually 90 degrees plus that angle. So if I redraw these two components, I've got this vector that is from 0 degrees. So if I talk about the Cartesian plane, here's 0 degrees. That's not what I wanted. Here's 90 degrees. I know that this guy here has an angle of and I'm just going to leave it in its complex form for the moment, the arctangent of 1/4. And then I'm going to take CD and I'm going to slide it up so that it's head to tail. And I know that, or maybe a better way to think about this is I'm going to take CD and I'm going to slide it over here, because what I want is I want these to share a vertex so that I can get an angle. Well, what's the angle of CD? If I slide CD here, the angle back to neutral, or back to 0, is 90 degrees plus the arctangent of 1/6. Now, if I want this included angle between the two of these, all I'm going to do is I'm going to subtract those two values from each other. I'm going to take 90 degrees plus the arctangent of 1/6 minus from it the arctangent of 1/4, and that's going to tell me the angle between the two of these. It's going to turn out, if it's 90 degrees, to be a simple problem to solve. If it's not 90 degrees, it's solvable, but it takes a few more, you got to jump through a few more hoops. So I think the easiest way to do this calculation is probably to use Excel. So let's set this up. So I'm going to say this cell is equal to 90 degrees plus, and then I have to say, in Excel, I have to say degrees, because Excel works in radians. And then I'm going to say the arctangent, and then I'm going to say 1/6. And it's going to tell me that the heading of that component is 99 degrees. Now let's go back to the PowerPoint and see if that's reasonable. So here's the question. Is it reasonable that the heading of component CD here is 99 degrees from 0? Well, yes it is, because it's certainly more than 90. It's certainly less than 180. And if I look, it's only a little bit more than 90. So 99 degrees is appropriate. So this angle here I can think of as 99 degrees. This included angle. Maybe I'll do that in a different color.
Hey, Ross,
So this included angle, 99 degrees.
I'm going to lecture for about the first 30
Now I got to find this angle here, which again is the arctangent of 1/4. So I'll go back to Excel.
130 is fine.
And again, I got to get it into degrees. Arctangent, 1/4. And that's going to be 14 degrees. And again, if I look at the diagram, this is reasonable. Now, the angle between these two is simply one minus the other. So I'm going to say take this number and subtract from it this number. And I'm going to find that the angle between these two is about 85.4 degrees. All right, so if I were to think about this angle here is about 85.4 degrees. Well, let's draw the end of component BC in a little more detail. So here's component BC, and I know that it's got this moment about it, 4,000 pound-feet. And actually, it's negative 4,000 pound-feet because it's in the clockwise direction. What I have to do is I have to produce a reaction that is perpendicular to that is sufficient to counteract that moment. Well, how long is this lever arm? Well, let's see. It's the hypotenuse of a triangle with one side that is 4 feet and the other side that is 1 foot. So if I think about it, it's going to be like 4 squared plus 1 squared. Take the square root of that sum is going to equal the length of BC, which is equal to, if I add those up, the square root of 17. So if I take the square root of 17, I get about 4.12, which is reasonable. About 4.12. So if I start thinking about